Bismillahirrahmanirrahim. Assalamu alaikum. I hope you are fine. So today here we have to continue from the last lecture which we have discussed yesterday. Just to quickly review what we have discussed yesterday, we started with the equilibrium data, and if you remember, we said that equilibrium data is important for designing of liquid extraction equipments. Then you have to continue with that, and we studied that when you bring in contact feed and a solvent, so various cases are possible, and out of those cases we picked two. One was when your both solvents are immiscible, and the other case which we picked, that partially miscible solvent. So here this topic actually which we are going to cover today in detail is partially miscible solvents. I just stopped my yesterday's lecture at this point, that why we go or why we are looking for this partially miscible solvents when we have discussed completely immiscible solvents like solvent present in the feed and externally introduced solvents. So that was enough, but why we are going for this? So I will just continue from same point. One thing more I just want to tell you here, that as I told you already, this is section 4.4 chapter 4 of Cedar and Hanley, chapter 4 Cedar and Hanley edition 4. So today by end of this lecture we will finish this section, and after this you can solve unsolved problem. One problem we have discussed yesterday, and at the end of this lecture there is a detailed problem about using of this system. So I will advise you to go through all those problems, unsolved problem, at the end of this chapter. So overall I will just introduce you briefly about this partially miscible solvent, and then we will discuss in detail about this system when there are partially miscible solvents, how we have to make calculations at equilibrium. This is major outline of this lecture, in which we have to discuss all that stuff of partially miscible solvents in detail actually. Right, this is from last lecture, this slide. So you remember that equilibrium data which we have picked for study consists of two cases. First case which we have completely discussed yesterday, and we have derived equation for this as well. We applied this to solve a numerical problem. So that was component A, that is of a feed, and that is solvent or carrier in the feed, and newly introduced solvent C, they are mutually insoluble, they are completely immiscible, they don't dissolve each other. So they are completely separated, and this is shown here in this diagram. I have discussed in detail. So next we also briefly discussed this, that component A and C are partially soluble in the single equilibrium stage when A and C, A is here solvent present in the feed, and the other solvent is externally introduced solvent. They are partially miscible when they are leaving this system liquid extraction equipment. At the end you have two phases, one is extract phase and other is raffinate phase. So when they are partially miscible, actually extract phase, I yesterday introduced you that extract phase is the phase which is rich in externally introduced solvent like C. This will contain this component C in very large amount, while this other solvent which was part of the feed, that will be available in very small amount here. And when you look at the raffinate, in the raffinate, it's that stream or that phase which contains very large amount of carrier, major part is carrier or solvent present in the feed, that goes to the raffinate side. As well it will contain very small amount of other solvent which was introduced here externally to remove this component B solute from this feed. So this system is very common. When you look at the practical example, this system is commonly used. So let's talk about this. Here in this system we start with this A and C. A is solvent available in the feed, and C is the externally introduced solvent. They are partially soluble in each other. What does this mean? Partially soluble, as I have explained in the last slide, that they can become part of each other in extract and raffinate phase, which was not possible when they were completely immiscible like the first case. But in this case they are somehow miscible with each other, so they will become part of each other's stream. And the component B distributes between the extract and raffinate phases. Component B is such component which is actually soluble in both, so it was part of the feed initially, and at later stages it is distributed just between the extract and raffinate phase. Some part is extracted towards externally introduced solvent and become part of the extract, while unextracted part remains as such as a part of raffinate. So this is the most commonly encountered case or a technique when you look at industrial example and the main of liquid extraction system. So due to this reason we are going to study this in detail, and most of the designs when you look for like designing of your liquid extraction equipments, you will encounter this case. So you should be familiar about this technique, and you should be able to make calculations wherever necessary. We can have different type of phase diagrams here actually in this system. By the way, before I jump to the next point, yesterday we discussed that when both solvents were immiscible, they were not soluble in each other, so we have derived one equation, and at the end of the lecture I told you that that equation is only valid when you have completely immiscible solvents, because in derivation of that equation we have involved some small parts of equation, and those equation contained that it is only like A is the part of only raffinate at the end of liquid extraction, and C was only part of like extract phase. But here in this case that's not the case, that's not the situation. Here we have different situation, so that equation cannot be applied. So we have to look for some other way, and that way is to solve such system using triangular diagram. And those triangular diagram are nothing, just they are the phase diagrams, phase equilibrium diagram between various components which we have as our part of liquid extraction data. So various diagrams, they are available from experimental LLE equilibrium data, and they can be used for designing of this system for making such calculations. So for example, here we are going to consider a ternary system. As we are studying overall ternary system, we said that we have to design ternary systems, and ternary system, you are very well aware about this, that ternary system are those systems which contain two components in the feed and one component as a solvent which is externally introduced. So here in this ternary system actually what you have is water and ethylene glycol. You can see here water is a carrier, this is actually our feed. This water plus ethylene glycol, this is our feed. So feed contain two components, it is binary mixture, and that is like in my feed there is water as well as there is ethylene glycol. So A, we represent this water with the A, and that's carrier, or you can call it solvent, and then there is ethylene glycol, that's represented with the B, and that's actually the solute. Solute is that part which we want to remove from the feed. And then there is furfural, that's represented with C, and that's externally introduced solvent to remove this ethylene glycol from our feed from water. And they are introduced into the liquid extraction equipment at 25 degrees C and 101 kilopascal, and he says which is well above the bubble point pressure. I will just talk about this point. So this water, ethylene glycol, and then there is something new maybe for you, furfural. So this is hydrocarbon aldehyde, so its formula is provided here. This hydrocarbon we are using to extract another hydrocarbon, that's ethylene glycol from the system. So what is bubble point? Bubble point is first of all used for the mixture. When you have more than one components, we don't call like something boiling point, we represent that with the help of bubble point. You already studied in thermodynamics. So bubble point temperature is that temperature at which first bubble is formed, first vapor is formed. You will have something in the liquid, and when first vapor is formed out of that mixture, that's called like bubble point, and at that time temperature is called bubble point temperature, and pressure corresponding to this temperature is called bubble point pressure. So overall, when you want to, suppose you have some mixture or even pure component and you want to boil it, you know that it will start boiling or some bubble will be formed when its pressure, partial pressure of that mean component, sorry, vapor pressure of that component is equal to the atmospheric pressure. So here we have 101 kilopascal, and he says that this is well above its bubble point pressure. So its mean pressure is high enough, so all your component here will stay in the form of liquid, none of them will be like vaporized. Due to this he has mentioned here that they are well above, this system is well above like bubble point pressure. So our overall system remains in the form of liquid, because we are studying here liquid extraction and we want to make separation based on liquid extraction. We are not looking for something like distillation or absorption, anything else. So here due to this we want that all of components in our system, in this ternary system, should stay in the form of like liquid. Due to this we have to provide them like at they should be at pressure that is below like their bubble point. Right, here in this system when you look at these, there were three components, as we said, there is water, ethylene glycol and furfural. So out of those, like initially water and ethylene glycol, they were introduced as a feed, then later you will have something extracted in the form of extract phase, that's furfural as well as ethylene glycol, and maybe water can be part of that. But before that, if we just make them like binary pairs, binary pair mean just they are two components or two chemicals in one pair. Here binary pair, one binary pair is this water and ethylene glycol, and other is furfural and ethylene glycol. So out of these two, this binary pair as well as this binary pair they are completely miscible with each other. Like water and ethylene glycol are completely miscible with each other. They were like looking in the form of one phase when we look at this, as well as furfural and ethylene glycol, they will also be in the form of like miscible liquids. While furfural and water, this furfural is solvent and water was also a solvent, so they are partially miscible binary pair. That we are dealing with those systems in which our solvents are somehow partially miscible with each other. So when we are looking at them as a partially miscible solvent, so here that's the pair which is actually partially miscible with each other and they are solvent. In this system, I have already told you that solute is ethylene glycol, and the purpose of furfural that's the solvent is to remove ethylene glycol from water, and we want to separate overall the ethylene glycol from water. Furfural rich phase is called extract. We have already seen this at the start of this lecture as well as in the last lecture, that before this you guys just introduced that phase which is lighter is extract and the phase which is heavier is raffinate. But yesterday I have told you to just revise that definition and get more technical definition of that you have externally introduced solvent, and in the system in which externally introduced solvent is in higher amount, like externally introduced solvent here is furfural, so furfural rich phase will be called as extract, and like water rich phase will be called as raffinate here. So we have to design a system like, or we have to make some calculation for such system, like yesterday when you were solving the system in which your solvents were completely miscible. So you have solved that system and you calculated the amount of solvent required. Suppose I have to calculate or I have to make such calculation in such system, in this system. So how I can make those calculation? Actually up to here I have just introduced you to a system, feed, solvent, and what is solute, how it is being separated, which are miscible pair, which are partially miscible pair, and how they will be separated from each other. Then now when we have to design such system, we will look for equilibrium data. So let's look at this slide here. You can see this is from your book, data, equilibrium miscibility data in weight percentage for furfural, ethylene and glycol water system at 25 degrees C and 101 kilopascal. These given condition which he discussed in last slide. So we are given with some data. kindly don't look at this diagram. I will explain each and everything to you. Just stay with me here. Like you can see, there is furfural, ethylene glycol and water. This is equilibrium data which is obtained from experiments. In the start we studied that for liquid extraction most of the data is available from the experiments. So here look at the first main row of the data. You can see here there is 95% furfural, 0% ethylene glycol and 5% water. What does this mean? That here when you have like pure there is no ethylene glycol in the system, while 5% water will be part of if there is 95% furfural. Suppose I just or you can say there is dissolution of water and furfural is 5%, while then as you keep on moving you can see that ethylene glycol is also part of that equilibrium data. Look at the last digits here. In the last row you can see that furfural is 7.7% while water is 92.3%. in this you can see that in water, if this is water rich stream, in water rich stream there will be only 7.7% furfural, and this is completely like furfural rich stream in which water is only 5%, while other data is provided. And by using this data, actually this diagram is plotted here, but I will just go through this step by step to introduce you how you can draw this diagram and how later we can use this for making our calculation, like calculation of raffinate, extract, as well as some other things. So overall, when I want to draw this data from this table, at least you are clear that you are dealing with a ternary system, so you will have three components. Excuse me. So out of these three components, if I have to plot these three on this diagram, so quickly just look here. Briefly, there is some axis like you can see for ethylene glycol, and then there is something for water, there is something for furfural. So these three are provided here. How I can plot them, how I can get that diagram? So we are looking at this. This is one triangle in which you can see that he has shown you three different color lines which are showing that actually I can plot some data here which is different from each other. Like if I have three different data, I can plot here, or I can locate them somehow. So overall I just consider, suppose this for blue lines, this axis, on this axis if I write something, some chemical, and these blue lines will be indicating to one chemical. Then these green lines, suppose I make this axis as my scale, like 0 to 100, for this as well 0 to 100. So here these are different lines of those, and then finally this is the axis for third component. Also for this we can make overall our axis from 0 to 100. From where you can get, as you have to solve various problem, as well as for practice purpose you will need such graph paper. So from where you can get this, book has provided this website from where you can download ternary system graph paper. I have provided direct link. Suppose if you go to this waterproofpaper.com and then graph paper, there are various types of graph paper you can download. They will be empty and later you can use them to plot your own data. So I have just provided you direct link for downloading such ternary plot data graph papers. So kindly download those, and when you are practicing you can use those. So here let's move a bit forward. Overall, when you will download those these graph from this website, you will look, there will be those graph paper are in the form of this diagram. Just ignore these colorful lines here overall, otherwise if I just remove these colorful line, I will get such graph. That is triangular graph, and there will be not mention of like these components, as you can see here, that DPA, diethyl phosphoric acid, then there is diluents and water. So these are just three components, consider them as 1 2 3. Overall, now you can see that there are numbers, as I have told you that in this diagram you can place number from 0 to 100. So overall, if you look at this axis here, you have number from 0 to 100. So 0, then there is something 10, 20, 30, 40 and so on up to 100. So just look, this is 0 for something, and then you see there is 10, then there is 20, 30, these are lines for these, then there is 40, and then there is 50 and so on up to 100. So this is the line of 100 for some component. So that component is water here. Actually this is axis of water, that is 100% at this point, and as you keep on moving in this direction, its value keep on decreasing. Some of they are a bit different from the graph which you usually use in XY, so just ignore that point. Like you will say, okay, this is starting from, but I think okay, it's fine, like it is starting from 0 and going towards 100, that's fine, like water is 100 here. Now next, like you can see something else, like for this DPA, I just call it briefly DPA. So for this you can see that at this point it is 100. So which line is indicative of this chemical? So here overall you can see that when you are reaching here, this is 100, then there is line of 90, there is 80, there is 70, 60 and so on. You will reach here 10, and then there is 0. Overall at this point this is 0 and it is increasing towards this. Yes, this is again same like as you have something on y-axis from 0 to 100. Other like look at this up. Now we have discussed up to here the two main component, but in ternary diagram you have 3 components, so third one is this one. So overall it is here, when you are here it is actually 100% at this point. So let's look at the lines for this. This is 100, behind this there is 90, then there is 80, there is 70, there is 60 and 50 and so on. You are reaching here 10, and then there is line of 0. So for this component here it will be 0 on this line. So overall one thing you can observe here, like they are called these points of triangular where two edge. I have these definitions later on, but just to tell you, this is called apex. This is another apex. Apex is actually called vertex or a peak or just one point. So overall like these 3 points of triangle are called apex. So you can see that like for water, and these lines overall you can say sides, which we call usually the side of triangle, they are edge, they are called edge here. So technically they are edge. So one edge opposite to this apex, suppose I look for water, the apex at which it is 100%, the edge opposite to that has 0 value. What does this mean? Like as I told you, water is here 100, then there is 90, there is 80, 70 and so on. Sorry. For water here, this is the axis. Maybe if it was confused in the last. Overall, these are the lines for, these lines are for this diluents, and for water these are the these lines. Overall this is 100, then there is like 10, 20, 30, 40 and so on. So let's look at few other diagram to make this point clear, but from this slide at least just remember that if you are given the simple plot, simple graph paper which contain like this triangular diagram, you can draw all three main components on that diagram, and you can locate any point. Right, look here, this is the diagram which consists of 3 components, which is water, acetone, and then there is trichloroethane. These are 3 components and they are being used here. As you can see in this diagram, he has mentioned here they are vertex, vertex, or we can call them apex, apex, apex. So vertex or apex is like some point, peak, anything. And then there are, he has called them base, which is I am calling as edge. Your book call them as edge, so just remember these are edge. These sides of triangle are called edge. So in this diagram you can see that you have 3 components. There is water, there is acetone and trichloroethane. From last diagram you remember that or overall as I have told you this point, that each apex or vertex or triangle is a pure component. Mean if we look at this apex of this triangle, they are actually indicating that here we have a pure component. At this point some component will be only 100%. When something is yes 100%, then there is mean no other impurity available there. You just look at the water, like here you have water will be 100%, and then for this, like this will be like 90% water, and then there is 80% water, and then 70%, and so on, and finally here I will have 10% water, and then when I reach here it will be like 0% water on this line, 0% water overall. And if I look for other like acetone, here acetone is 100%, then this is like for 90%, 80%, 70, 60, and so on. If you keep on moving, here there will be like 10% acetone, and this line indicate then there is 0% acetone. Then the third one here trichloroethane. So for this is 100%, this is 90%, 80%, 70%. You keep on moving, then you reach to this 10%, and finally here this trichloroethane is 0%. Why I am repeating again and again? Because later you have to plot these you will have just simple lines, and you have to plot your data. So you should be able to read, or you should be able to mention what is that point and which line indicate which component. So you should be aware about this. Due to this I will be keep on repeating this stuff. So overall, now as you know that these apex are indicating your pure components. So as you keep on moving to the edge opposite to that apex, suppose this for trichloroethane, edge opposite to that is this one. And here as I said that this line, final line, this line indicates that there is 0% trichloroethane. So overall, when you have 0% trichloroethane, so it's mean there will be two other component which will be part of this line. Due to this, he has mentioned here that this edge indicates a mixture of two components like water and acetone mixture. Due to this, he has mentioned that each edge in a triangular is a mixture of two pure components at the terminal apex of the side. Like here, and I have like apex on this terminal and apex on this terminal is acetone, and apex on this terminal or apex or vertex you have this water. So overall, if I just draw a line between acetone and water, so it will be a mixture of acetone and water, as you can see here, water and acetone mixture. And you see that here we have pure water. When water is 100%, there is no acetone. So overall at this point you have 100% water, and you move to this line. What I told you, this line mean 90% water, and when there is 90% water, what will be the amount of acetone? Definitely 10%, and you keep on moving towards acetone, definitely amount of acetone will keep on increasing and water will keep on decreasing. And similarly for other, you can also see here edge opposite to water apex is this, and edge opposite to this is this one. So here you know that water is 0%, here it's 100%, you will keep on moving and finally it is 0%, and similarly for acetone on this side. So this is all about this diagram, like if you are reading these lines with respect to one component. But if I just look at any component in between, like any point located within the triangle, so what does that mean? That means ternary mixture. Suppose I just look at one point here inside. So we will look at this in next slide, that how can we read it, that what is the composition of this point actually. So just to make those points more clear, which I have discussed in last slide, so overall just look here. This is the same mixture, same system we will continue with. So overall this is trichloroethane, and you know that is at this point trichloroethane is 100%, and as you move away from this towards opposite edge, here this is opposite edge to the trichloroethane. So this is 100% and it will keep on decreasing, and I told you that at this line when there is a mixture of water and acetone there is 0% trichloroethane, which we were discussing in last slide, so it's again mentioned here. So definitely when there is only water and acetone there will be no trichloroethane here, so it is 0%. So you can see here that that's 0%, then there is 10%, 20%, 30%, and then 0, 10, 20, 30, 40 overall. I think one line is missing here. Then there is something, this 50%, 60%, 70%, 80, 90, 100. No, he has mentioned actually at the wrong location. This is 40, not 50. Just make it correct. This is 40. Then there is 50, and then 60, 70, 80. This is line of 90%, and then this is 100% overall. So similarly you can look for the water. Suppose we look or not water, like I have discussed water in last slide, acetone. Look, acetone here is 100%, and if I just look on the edge opposite to this is the edge opposite to acetone. So edge opposite to acetone, what is composition of acetone on this edge? 0%. Due to this he has mentioned here it is only water and trichloroethane mixture at this line, and acetone will be 0 here. When acetone is 0, so as you jump behind this, there is 10% acetone, then there is 20% acetone, 30%, 40, 50, and this line is actually 90% acetone. You can count from here 100%, 90%, 80%, and then there is 70%, and so on. You will read to this 0%. Because when we have to allocate our data, we should be aware about this, that inside diagram you have a mixture, but at what does these apex mean, or what does these vertex mean, and what does these edge or side of triangular mean. Each edge is a mixture of two pure component, as we already know. So just look at this here. If I just select this apex here, it is pure acetone, and if I just move along this line, which is a mixture of acetone and TCE, trichloroethane, so along this line, you know, this is a mixture at one of the apex of this line, or I can say end point, terminal point of this edge or this line. On one end you have 100% acetone, and other end you will have 100% TCE, trichloroethane. In between, let's look at them. Suppose you are just counting and you want to look in between. So look at this point here. He has mentioned this is acetone 50% as well as TCE is 100%. Quickly look at this, that either it is correct or not. So if you see here, this is 100% acetone, this is 90% acetone line, then there is this line, this is 80%, 70%, 60%, and definitely this line is like 50% for acetone. So it's mean when point is located here, it is like 50% acetone. So now we are on edge, where like component opposite to this edge, that is water, where it is 100%, like apex at this apex, so that is 0. So if one thing is 50%, so other component only, like acetone is 50%, then there will be TCE, that should also be 50%. So let's look at that, either it is 50% or not. So if you remember, this scale is for water and this scale is for like acetone, and this scale, this one is for our TCE. So for TCE you can see these lines in this direction, you can see TCE. Here you see TCE is 100%, so the line here for this 90%, then there is 80%, there is 70%, then there is 60%, and this line is 50% for TCE actually. When there is 50% line and you are available at that point, like here at 50% at this point, so definitely TCE is 50%. Now similarly you can read for the other points. Suppose you want to look for water acetone mixture, and you are looking for like water is 70% and acetone is 30%. so quickly look at this, like water is okay, just consider like water as 30% and acetone as 70%. we will quickly look at this. Just try to locate please where will be the point, then I will tell you. First of all, when you have to locate it, locate for the water, like water should be 30%. you have to locate the point where is as we are having here water and acetone only, 30 plus 70 it's mean 100%, so no other component. So you will just ignore like other component, that is TCE, only look for water and acetone. Out of those, just look for water first. Water, like if I just start from here, water is 100. So quickly now, if you know already remember, this is this line, this is 10% for water, this is 20%, and this is 30% line for water. So here my point will be located here. Now I have to locate 70% acetone. How you can locate? What are the lines of acetone, or where lines of acetone are located? You know that these which are like horizontal line, they are for acetone, and acetone here is 100%. you see, then there is acetone 90%, acetone 80%, and acetone 70% line. So you remember already we have marked this point for 30% of the water, as well as same point will be marked for 70% of acetone. So this is the point for given composition. Hopefully you have located it correctly, otherwise just try again. Right. And now we have to look for some point inside the diagram. Actually I have to look for some point inside diagram. As you are aware about this, that like you have to look for apex, or you have to look for edge. You can locate the point. But now if there is a ternary mixture, ternary mixture is a mixture which is or which consists of actually more than one that is available inside diagram, not on the edge, not at the apex, that is available inside the diagram. So how you can read that point, how you can locate that point? So overall just ignore this diagram. I will explain these two, and out of those just start with this. Like here you can see you have acetone as 46%, water is 32%, and TCE is 22%. so it's mean, what does this mean? There are all three and they are completely making it like 100%. it's mean this point will be available inside this our diagram. So if you have to look for inside, overall just locate for each of these. Here we have to locate for 46% acetone. Let's start with this. For acetone, you see here what is the amount of acetone here. I think you remember now, it is 100%. So I have to locate the line of acetone which is at 46%. so just look, this is 90, keep on counting, this is 80, 70, this is 60, and then there is 50, and this is 40. so as we have 46%, so line will be located inside somewhere. So due to this, he has drawn here green dotted line, that is indicated of 46% acetone. Now this is just one. Here in this diagram actually I have drawn all these three, and you know that this is our point. But when you are looking for some point, or you are going to draw some points, just locate in this way, that like first one I will locate where the line of acetone for given composition will lie inside my system. Then water, okay, look for water. Now you have to locate for 32% of water, and you know here water is 100%. then water will keep on decreasing as you keep on moving away from this apex. So water is 90%, 80%, 70%, then there is like 60%, 50%, 40%, and this line is 30%. as you have 32%, so this red dotted line is for water at 32%. Overall, maybe you will be wondering how you will count. So this is just somewhere here it is middle, that is 35, and you can just draw like somehow away from 30, that's 32%. mean at this point this green and red will just intersect each other, but still we are left with something that is called TCE, and for TCE you have to select line at 22%. So like start from here, you have now TCE is 100% here, 90%, 80, 70, 60, then there is 40, 30, 90, 80, 70, 60, 50, 40, this is for 30, and then there is for 20. So we have 22%, so it will be somewhere located here, that green dotted line. So overall the point at which these three will intersect is our given point. So that's, you can see here, that's located inside diagram, as I told you that in the last slide, that any point where there are like 3 points, and it's been our composition of all 3 components is given for some system, so it means that point is located inside the diagram. So we have located it. Similarly, at this stage just still ignore please these curve and some other black dotted lines. I will explain them on later stages. So another similar diagram you can locate these points. So that's for solute, solvent and carrier. So where they are mentioned in this diagram, they are mentioned here. Solute is 100%, then there is this is solvent, not solute. This is solvent is 100% at this point, there is a solute at this point, it is 100% at this point, and then there will be lines for this, and then there is a carrier that is actually 100% at this point. So similarly here actually the inside lines are missing, so due to this maybe you can just quickly draw them and can locate where your point will be located. So just try it this way, similarly as I have told you here. I will quickly just tell you one thing for this, that's like for carrier, where carrier is 100%, you can see carrier here will be 100%, and then there are lines for this carrier like 90, carrier 80, 70, 60, then there is the like line of 50, and then there is 40. So as you have it like 0.48, so it is somehow here close to 0.5, like at 0.48, this green line, this is for carrier. And similarly you can draw for other solute and solvent, and then the point at which they will join each other, that's your given point. Sorry, somehow slides are mixed, the slide was repeated, same actually this was the slide, last slide contain another diagram, so that was not related to this. Here the same is presented, which we have seen in the last slide, that like you have 3 components, acetone, water and TCE, how you can locate them, as well as here solute, solvent and carrier. If you are given composition of all these 3, it means their point is available inside this triangle, so you can also locate that. So now up to here, what you have seen is actually now you are familiar what triangular diagram is, and how I can mention component of my ternary system, like 3 components where they are like 100%, how they are varying, how their scale is varying. Up to here this I have explained to you. And if you recall where we jumped for this main system, when we have one table in which I told you that this is the equilibrium data, and then there was one complex diagram which you have seen. So that was drawn, but I told you that let's go through few steps, so you will be able to draw that diagram. So now we have reached to that point. You know already that like how you can read this diagram, how you can locate various components on different scales inside this diagram. So let's look at that table and diagram now. Like here, this was the table which I have shown you, and I told you that this is the first row of this, indicating that miscibility of water in furfural rich stream, and then there is last row has indicated that miscibility of furfural or solubility of furfural in water rich stream. So overall, if you observe this data, that's indicative of 2 things. Like here, some part is furfural rich, Why? Because overall there are two solvents. There is furfural is one solvent and water is another solvent. So if you look at this main furfural and water system, these are two solvents, and mean amount of both is like varying when you are just moving down through this data. So when you are moving down through this, overall you can see that here the amount of furfural was maximum and then it is decreasing, while water initially was in small amount and then somehow it was still reduced, but later it start increasing. And when you just cross this point or up to here, up to this point, we will just can see that up to this point furfural is higher in amount as compared to water, and we will call it like furfural rich data stream or furfural rich equilibrium data. And the other side you can see that as you jump at that from that point, like where water was 20%, now you can see water is 38.6%, while at this compared to this furfural is now 13.9%. So in this system you can see now this is water rich system from here to onward, like still furfural is decreasing till end and water is increasing. So this data is of this can be divided into two parts. Overall this is given here in the book as a single table, but that can be written as like furfural rich data or furfural rich stream, and then there is water rich stream data. This was okay if you just look as a single table, but in your book when you will look at some unsolved problems, you will see that data is just distributed in this way, like furfural rich and water rich. So don't just get confused with that. That's you can see that somehow similar data just represented as a side by side table. In one they have shown like furfural rich, and the other side here they have shown water rich. So that's the same data. Due to this I have explained here. Now using this data you can draw this diagram. Inside this diagram, what is different from that which we have discussed so far? Overall you can see that there are again the three sides of this triangle or three edge of this triangle, and then there are three apex of triangle. Overall if we just start from here, there is water, that is solvent. And by the way, from where these came, water, furfural and ethylene glycol? We started with one system initially, in which you have a feed stream. There was water and ethylene glycol, and you have introduced a solvent to remove ethylene glycol from the water, and they were introduced at 25 degrees C and 101 kilopascal. We have discussed few minutes back. So here that's the same system, like water. You can look at here is a water, then there is ethylene glycol and furfural. Like water here at this apex is 100%, and then there is 90%. They are given in the form of fraction actually. So overall, as I told you earlier, that this scale is showing here 90%, 80%, 70%, 60%. These lines mean at this angle, which will be like somehow like 45 degree. So you can see here it is given mass fraction of water. So this is scale for the water, this scale. Then look at ethylene glycol. For ethylene glycol, what you can see here, ethylene glycol we have like these. This is 100% here, then there is ethylene glycol 90%, ethylene glycol 80%, ethylene glycol 70%. So they are given like 0.9, 0.8, 0.7, and then finally you will reach here 0.1, and then finally this is 0% overall. So this scale is for ethylene glycol. They are given actually these for horizontal lines. Their scale is given like 0.9, 0.8, so and so on. Then third one here is furfural. Furfural is here 100%, or its fraction will be 1. Then there is like this 90%, then there is 80%, and so on. Overall, when you will reach to this angle, this side, this side, which is just opposite to this apex, there it will be like 0%. And its scale is given here, like this mass fraction of furfural. This is the same stuff which we have seen for other components in previous diagrams, but we didn't discuss something created this insight. overall inside this diagram, when you have located these main axes, you know your axes and which axes are which line, like some lines are available at more than by the way, as I told you that for water these lines of this scale are at 45 degree, and for this furfural you can see that they are higher than 90, so they are somehow like at 130 sorry, or 130-35 degree for degree angle, and these are just horizontal line which are like at 0 degree, they are like for ethylene glycol. Now when you have located them, and you can look from here, from this data, you have to plot that data actually. You can just download from the website which I have mentioned. There will be some triangular this diagram in which there will be similar lines, like there will be horizontal line, there will be lines at 45 degree angle, and they are at like 135 degree angle. So just mention your component at that graph paper, at that triangular diagram, and then when you have mentioned that, like this point is water, this point is ethylene glycol, and this point is furfural, now I have to locate my points. Based on that, I have to draw these lines. Overall, at this point, based on this given data, we can draw this line, this way on which we have like something miscibility boundary curve. So how we can draw this miscibility boundary curve based on this given data, equilibrium data? Just look, first point, there is like 95% furfural, 0% ethylene glycol, and 5% water. Just tell me where I can locate this point. Overall, you see one important thing here, there is 0% ethylene glycol. Can you locate the line where it is 0%? I hope you can easily locate the edge opposite to the apex of ethylene glycol. This is apex of ethylene glycol, edge opposite to this is here, this line, just bottom line. So here ethylene glycol is 0%, you know. When ethylene glycol is 0%, now you have to draw the point like 95% furfural and 5% water. So this is overall this line, when 0% ethylene glycol, that's actually furfural water mixture line. On at this line, you can see here you have 100% furfural at this end, and you have to locate 95% furfural, so it will be like some point here, 95% line. And now you have to locate the line of water, that is like 5%. So where water is 5%, here you can see that for water we have the lines at actually 45 degree angle. So water is like 100%, and as you keep on moving away from this apex, you are decreasing the concentration or amount of water. Overall, you can see here this line which is mentioned here, joining here, that is actually like 10% for water. And if I just draw another line after this, like that will be 5%, and that will just come here somehow. If I just draw straight line, so that will cut here somehow here at the same point, and where you have this point, starting point of this curve. Clear? This is one point I will just locate, and then now look for the like just last point of this, then I will just explain 1 or 2 points inside. So last point here you can see that is 7.7% furfural and 92.3% water. So when now look at this, like same, this will be the same line here we will be using, because again ethylene glycol is 0 here. That's the easy one to locate. This is the last line. Yes, overall you can see here like that water is like 100%, and then there is water 90%. So overall you have here 92.3% water. So that line will be somehow here 92.3% water, and I have to draw the line of 7.7% like furfural. So you can see here furfural was 100%, and you keep on moving, so there you reach where furfural is like somehow 10%. So this line for furfural, this here you can see like at this point furfural is 10%, because this is scale of furfural. Here you can look here, please don't get it confused, like here it is 90%, so this is line of 90%. No, this is just for scale for this horizontal line ethylene glycol. So for this furfural, this is 10% here, so we are looking for 7.7, so definitely there will be some line just moving away from this point. Like here, this will be straight line of 7.7, so where this 7.7 and 92.3% line cut each other, so here you can locate that point, and that's the start point of our like curve here, another point. Clear? So after this, just like you can go to any other point. Suppose let's locate one, right? You can locate here any point, like that is 44.5% furfural, 44.5% ethylene glycol, and 11% water. So just let's locate this point. Where does it lie? First of all, we will look for furfural, that is 44.5%. so furfural, where is the axis of furfural? This is the axis of furfural, and that's the 40%. Then there is 50%, so in between there you can draw a line like for 44.5 here somewhere. Not straight, but just you can get the idea that here will be line of furfural 44.5. Now next, ethylene glycol, like actually I have to locate one point. Finally I will be locating the point. There was one point here, and then I have to locate all the points and then join them to get this curve, that is somehow miscibility boundary curve. For that, to locate those points, I am just drawing this line. So later, like you can use lead pencil, you can draw these points and lines, and later you can just remove them when you have just located your point, intersecting point of all these three. So first furfural 44.5 we have. Now ethylene glycol 44.5. just look for the axis of ethylene glycol. This is axis of ethylene glycol, horizontal line, just drawn quickly. So just properly draw these lines with the help of like ruler, and at the end there will be one intersection point of all these three lines. So that intersection point will be actually one point of your this curve, and so on. You can draw them. Please practice this. Just download one of those figure, print that triangular diagram, just mark your points like this, your these components, and then try to just redraw this diagram. In this diagram you can see that like okay, if we keep on moving, just putting these points, finally you will join them and you will this get this curve, that is called miscibility boundary curve, or also called it like binodal curve. Binodal curve, if you remember from thermodynamics, binodal is a curve that actually separates like one phase from the two phases. So overall inside this diagram, somewhere we have one phase and somewhere we have two phases. We will look at this just in few minutes. Okay, inside this diagram, now for your practice, there is one point M. You can see here there is M. Just try to locate or try to find the composition of M. Can you find the composition of M? If you have understood all the topic which I have just told you up to here, then definitely you can locate M, and what is the composition of M, you can easily find that. When you have found that, just compare with the composition provided in your book. Textbook provided of M, composition of M is provided. When you have calculated on your own from this diagram, then just go to the book and compare it with the composition given in the book. Okay, any above this binodal curve or miscibility boundary curve, only a single phase exists. As I told you that binodal curve is actually curve which separates single phase from the two phases. So above this curve there will be a single phase, and below this there will be two phases. So let me just show you one other diagram. Just look at this. Overall this is our same system. Here you can see that above this was miscibility curve. Above this miscibility curve you can see that there is a single phase region. What does this single phase region mean? In which this means that you will have all these three components, ethylene glycol, there will be like furfural and water, and they will be existing in a single phase. They will be miscible with each other and they will exist in the form of only one phase. But below this miscibility curve, inside this region, actually there are two phases. And what are those two phases? Actually they are extract and raffinate, and you can just separate them. You can find their composition if you give them time for equilibrium, they will just will be separated into the raffinate and extract. So here two phases exist actually, one will be rich in furfural and other will be rich in water in this region below this miscibility curve or binodal curve. Okay, one thing more here we didn't explain, or up to here we didn't touch in this diagram, and those are some dotted lines. Here you can see these dotted lines. So let's look at those dotted lines. They are actually called tie lines that connect the points on miscibility boundary curve. Let's look at them, how they connect and from where we have drawn them in your book. Here some data is presented in one table, that is like data for glycol in water layer percentage and then there is glycol in furfural layer weight percent, and if we have those, we just join them. Overall you will get something like these tie lines. So how you can draw them, or how you know the percentage of ethyl or something like glycol? You know that glycol is extracted from water towards furfural. So overall here, like when we have glycol in water, it's mean that's our raffinate phase, and then there is glycol in our furfural layer, that is extract phase. So overall you can see here there is mentioned something called extract on this side. Here you see this side is actually rich in furfural. So on this side actually we have extract, and other side we will have raffinate. So you will just locate these points on those sides, and just you can join them with each other. Based on that they have just provided us or given these tie lines. So each pair of points represent the composition of equilibrium phases. What are equilibrium phases? Like equilibrium phase for any given point in the raffinate and equilibrium point in extract. Suppose you look for some out of these, as I look for like 41.5% of glycol in water and 41.5% of glycol in this furfural. So this is one pair, so that is indicating that at some given point somewhere inside this diagram there will be like 41% glycol in water and 41% glycol in furfural, and that's the main equilibrium phase or composition of this equilibrium phase. Right. Next we can look inside this diagram, like if you are given any mixture, suppose here we have a mixture which contain, mixture mean that contain feed as well as solvent. When you have just mixed them, you have brought them in contact with each other, and finally you want to make some separation based on this liquid extraction. So if that mixture is like 20% ethylene glycol, 19% water and 61% furfural, shown as point M. Here there is in the diagram you can locate, there is point M. I think you have already practiced this as I asked you earlier. So you know, you have found the composition of M, and that will be similar to this composition given here. So overall this is like 20% ethylene glycol. So we will quickly look, either it is 20% ethylene glycol. So you know, for ethylene glycol these are the horizontal line, and horizontal line axis is this point 2. Here you can see just this M is located on this line of point 2, that's mean ethylene glycol is 20%. Then there is 19% water. So water was here 100%, 90%, and overall this was 20%. Line available at like this line was available at like 19%. So here yes, it is 19% point, and then there is something 61%, and that is furfural. So overall let's look at this, either it is 61%. So yes, this is the line of furfural 60%. So our point M is located at 61%, that's fine. So mean all these three will be intersecting, and this is point M given here. So when this any mixture which is brought to liquid extraction equipment, so when you bring it to like equilibrium, the resulting composition of equilibrium extract and raffinate phases can be measured from here. Like I brought this mixture to the mixing equipment, in liquid extraction equipment, and that contain like there is a mixer, and then you give it some time for settling. They come in equilibrium with each other, they get separated into two phases. One is extract phase and other is raffinate phase. So we can actually locate those composition of extract and raffinate from these diagram. That's actually the application of these diagram from where I started, mean that you can use these diagram, these system for designing your liquid extraction equipment. Suppose you are designing some liquid extraction equipment, and someone give you that this is my composition, I want to separate this. So what will be final composition of extract and raffinate in my case? So how I can find? I can use such diagram if I have the data, equilibrium data for these systems, of your system. Then you can draw such diagram and finally can find the this composition from this diagram. So let's look at this, how we can find. Overall there will be point M, then by using from point M you have to draw the tie line. If this point is already, M is already on a tie line that is given here, so I can just locate two ends of this tie line. Overall you can see, now I will just draw a line here. This is this dotted line which is passing through M, or M is located on this line, and its two ends are like, one is here point R, that is on raffinate side you see, and then there is point E, that is on extract side. So here on raffinate and extract side you can see the compositions. If I am looking for the composition of extract, can I find? Yes, here extract is found to be like 10% ethylene glycol. Before I just read from there, you can just locate from here on your own. Here this is E point, and E is located on 10% ethylene glycol. Just look for something. This is the axis for furfural. So furfural is like between 80 and 90, and it will be like somehow 86%, I think around. It should be like 86% here, because line will be like here somehow 86. And then you can look for the water. So overall now, as composition is 100%, one is 10%, other is like 86%. You can see that water will be 4%. Otherwise you can just draw line for water, and you can read from here that either it is like 4 or 5%. So from here you can see that like 86% furfural, 4% water, and 10% ethylene glycol for this mixture will be obtained when you just get it separated like extract. Similarly, like for raffinate, let's look from here for raffinate. First of all, look for ethylene glycol. It is located on 40% line. This is 40%, so there will be 40% ethylene glycol. Now this point for water you see there is this is water scale, there is 50%, so it is just less than a 50%. I think it will be like 48%. So you will write like 40% ethylene glycol, 48% somehow like water, and then left like will be I think somehow 12% like your furfural. So here he has mentioned like 49% water. If he is taking 49% water accurately, then there will be definitely 11% furfural. So you can see from here like how either it is exactly 11 or 12% or not. So you can see there it is 10%. So if you just draw a line for this, you can locate either it is 11 or 12% furfural. Right. One thing more here, suppose our point M at this for this given mixture was located on the tie line, but suppose if your point M was located somewhere here, like M is located here. Now how I can draw the tie line, or how I can just join 2 points to E and R? You have to then there is no tie line in between. You have to interpolate tie line. How you can interpolate? Like you can just draw a tie line in between the given lines. So that that finally pass through this point. Suppose this is my M point, so I can just draw a line which just reach here as well as it reach here, and somehow I am just drawing M in between these two. So here it will be located in between two dotted line on this side, and as well as it will be located somewhere here on this side. Overall just you will draw with the help of ruler just straight line. So then you will read the composition of your extract and as well as raffinate from this miscibility curve points by looking for the axis of all three components. Hopefully this is clear to you. So let's jump towards example. By using all this stuff, we have to solve one example. Right, before I just start this example, there was one point which we have missed somewhere. So let's go back there and yes, here. Yeah, when we were discussing all this stuff overall, now you have seen that there is a curve which is called like this binodal curve, and there is one point on this curve that's called this plate point, and this plate point is actually a point where your tie lines will meet. Overall, if you have seen, there were values of tie lines. You have seen from the table that they were reducing, and finally they will reach to a point that they merge with each other, and that's called actually plate point. And after this plate point, then there is no other tie line. So that's one point was missed. And here you can see that plate point where the two phases become one. Overall, you see that here we have two phases below this binodal curve, and after, as I told you, that then there is one phase. So that's like the point where your system will have one phase. So you can also call this plate point. And now let's start with example. So here example is from your book again. So I will solve this completely here for you, because there are several problems related to this and this important one. So kindly right here I'm going to solve this example completely, but I will advise you just to solve this on your own when you have just gone through this, because we have discussed we will discuss this, but this involve various unsolved problem, they involve same concept. So I will just advise you to go through all this stuff and solve on your own, so that you can solve those unsolved problems. Let's read this, that this example is about single equilibrium stage extraction of ethylene glycol. Here what we have to do, determine A part here equilibrium composition, and B part amounts of extract and raffinate. What is purpose of this example is to find the equilibrium compositions of extract and raffinate, and then also amounts of extract and raffinate when a feed F of 100 gram of 45 weight percent ethylene glycol, 55 weight percent water is contacted with 200 gram of solvent of pure furfural at 25 degrees C and 101 kilopascal using data in figure 4.13. So figure 4.13 is the same figure which we were just using in last example in all discussion. So that figure you have to use, that's from the book, and on that actually already binodal curve is plotted, so we can quickly use that diagram. Suppose if you are given other data, you can also draw the similar diagram and can use that for your own system. So this is the question in which you can see that your feed contains two components, that is ethylene glycol and water, and their percentage composition is given as well as amount of feed is given. Here we know the solvent is furfural, and that's represented with C here. Water solvent or carrier in the feed is represented with A, and ethylene glycol is represented with B, and the amount of solvent is 200 gram, and that's pure. Pure mean it is 100% furfural, there is no other impurity and neither any component from the feed is part of this. So let's solve this. First of all, here data, what data we have from this statement. Overall you can see that we are given amount of feed, this is given to us, that is 100 gram, and then you have composition of feed, that is 55% water and 45% ethylene glycol, that's total 100%. And now just when you have something 100 grams, so it is 55%, it means there will be 45 gram of water, and then there will be 55 gram of water and 45 gram of ethylene glycol based on this. And at the same time you have solvent, that is 200 gram, and its composition is 100% pure, mean 100% furfural, and I am represented it with C. This is the data which is provided. As well there was something that was temperature and pressure was given to us. You know that based on temperature and pressure this equilibrium data varies. So suppose you are solving some problems and you know the temperature and pressure, so your data should be provided on that temperature and pressure data actually for drawing that diagram, that miscibility curve. So here we have already data was mean on the same temperature and pressure. We can use that same similar diagram. What is required, what is asked in this question, as I told you that you are asked actually two things. One is amount and composition of extract, as well as amount and composition of raffinate. So overall you have to like measure I think 4 parameters, like amount of extract, composition of extract, then there is amount of raffinate and composition of raffinate. And you know extract and raffinate are two phases when system will reach to the equilibrium and they will be separated out. So just let's solve this. So in order to solve this, first of all, to reach these main final conclusions, we have to go through some steps. So first step is here. First of all, you will find the amount of mixture, because you know that in our system where we have a mixture, mixture will come from actually feed and solvent. When feed and solvent are contacted, feed and solvent come in contact with each other, so definitely a mixture will be formed, and that mixture will contain like water, ethylene glycol and the solvent. We pass this mixture through a mixing element, and so that extraction takes place, and then you give it time for settling, separation at equilibrium. So that amount of mixture, as I told you that this mixture is formed from feed and solvent, so what you have to do, you have to just add them up. So your feed will be amount of mixture will be equal to amount of feed plus amount of the solvent, and you know that they were like 100 and 200, so overall this will be like 300 gram amount of mixture. Next, this clear, hopefully clear to you that mixture is formed from our feed and like solvent, so that will be total 300 gram. And then you have to calculate the composition of the mixture. Actually why I am calculating this, later I have to use in some next step like amount of mixture. So composition of mixture, what does this mean, composition of mixture? As I told you that mixture will now contain feed as well as solvent. So feed contains water and ethylene glycol, so overall mixture will have water, ethylene glycol and furfural. So we have to find their percentages, composition. You know that composition means something in fraction or percentage. Like here overall this mixture is formed when we mix feed and solvent, and it will have, we have feed and solvent, and it has like 55 gram of A, 45 gram of B and 200 gram of C. As I told you when I was just explaining this here, and like given data, so water is 55%, so it will be like out of 100 gram it will be like 55 gram, and then there is B is ethylene glycol, that is 45 gram, and overall like 200 gram of C. So these are the three components of mixture, and we know their amounts, but what we are looking for the composition, their percentages. Why we are looking for those percentages or composition, by the way? Actually we have to locate our mixture point or composition inside that diagram, and you remember that the diagram which we have to use, we have just discussed, that contains something like in the form of percentage or fraction. So due to this we have to convert all this data into percentage or fraction. So here fraction of A, how you can find the percentage or fraction of A? Now you know the amount of A as well as you know amount of the mixture of which A is the part of. So overall you can find it like fraction of A in the mixture will be equal to amount of A divided by total amount of mixture. Amount of A is 55 gram and total amount of mixture is 300. So when you just divide, you will get either 0.183 or 18.3% like. At the same time, you can also calculate B in the similar way, that is amount of B divided by total amount of the mixture. So just please solve this on your notebook while you are going through this. Each step should be solved on notebook. So amount of B is 45 gram and then there is total amount of mixture, that is 300 gram. So you can get here like 0.15 or 15% of the B in this mixture, and then there is like fraction of C in the mixture, and that will be like amount of C divided by total amount of the mixture, and that amount of C is like 200 because you know that here we have amount of solvent as 200 grams, so 200 divided by 300 and that will be like 0.667 or 66.7%. So overall up to here we have calculated the composition of a mixture. We know that how much amount of A is part of this mixture, how much like amount of B and how much amount of C in the fraction or percentage are part of this mixture. So now let's look at all these like feed which was given to you, that based on its composition you have 55% and 45%, and then you have solvent that is 100%, and now you have calculated all these three A, B and C their amounts in the mixture. So let's look at these feed, solvent and mixture in the diagram. Yes, this is the diagram. Overall before I look at those points in the diagram, I can show you this is equilibrium stage in which you are introducing your solvent and the feed, and when they are coming here in contact with each other, you are then finally getting extract and raffinate. So out of this, like you can see that finally we are getting extract and raffinate, and this is the diagram from your book, but I have taken the similar diagram from some other source with a more clarity. Overall you can see this is the same repeated one. Just look here, this is the feed and the solvent, and inside you can see that feed is, he has mentioned kilogram, actually this is the gram like, and this is 200 gram, and out of that you see that A component was like water. Here he has mentioned actually C component, water was 50%, and then there was furfural that was not part of that, and then there was actually ethylene glycol that was 45%, and at the same time you have solvent that is 100% like furfural. So here that's mentioned that its fraction is 1. Overall he has mentioned just so that you can easily locate all this stuff on your diagram. First of all, as I told you, I have to locate solvent, feed and mixture inside this diagram. Solvent, your solvent was 100% pure furfural. So where it will be located in the diagram, you can see here furfural is 100%. So my S point is located here, due to this he has mentioned here S point. Clear? It will be located here, we will locate S point. Now solvent is located, you have to locate feed on this. So your feed is located here because feed, you know, feed does not contain any furfural. So where is that point where there is no furfural? This is the line where furfural is like 0%, just opposite to this apex of edge opposite to the apex of furfural, to the this vertex of furfural, and that's this line. On this line this is 0%, while you have ethylene glycol and water only, and out of those you see that water was 55%. So this is the axis of water. On this axis you can see this is 50% water, and then there is 55%. So this is your point of 55%, and after this you have to look at 45% ethylene glycol. So overall for ethylene glycol as 45%, where it is, yes, you see here ethylene glycol 90, 80, like here it is 50 and then there is 40. So overall, like you can see, there will be some line here 45%, so it will be just matching here, and you can get here your feed will be located. Now after this you have to locate your mixture point inside this diagram, that will be inside definitely, because that contain mixture. You have seen that composition of mixture, and that composition of mixture contain all water, ethylene glycol, as well as there is furfural. So all those three can be located inside this here at the M point that is given inside this diagram. You can locate all these water, furfural and ethylene glycol, and they all will be intersecting at this point M. And overall you can see finally that if we just draw a line from solvent to feed, like this was solvent point and there was feed point, that will be definitely pass through the mixture. So your mixture will be located on the solvent and feed line. Definitely it will be located here, because from where this mixture is coming from, this mixture is coming from same solvent and feed. We have mixed actually feed and solvent, and then we got that mixture. So definitely that mixture will be located on the line between these two, solvent and feed. So this was our purpose here up to this point, to locate these three. Now you have located hopefully all these three on the diagram, on your diagram. Next, after this what you have to do is the fourth point. Next, from this point M, draw a tie line towards binodal curve. Now when we have located our this mixture point M inside diagram, next is like from few slides back you have seen that I have told you that if you know the M, you can from composition of the mixture, actually you can draw the tie line towards the both end of the curves from this, and from that what you will get is the raffinate and extract stream in their composition. So overall if I just draw one tie line from here, and if as in this case M is not located on the tie line, so you can draw, or you can like interpolate tie line between here, like you have above and below tie line is there, so you can just draw a tie line, and that will be that will connect on the point E and R on binodal curve. So let's look at this here, and then when we have located point E and R on that graph, you know, from E and R point I have told you, like we can get the composition of E and R as we have done few minutes back. So yes, let's see here. There was M, and we have drawn a tie line here, this red color line that is shown here, and that is one ruler is placed just to draw a straight line here. So you can see that it is connected at the point R and E on the binodal curve or miscibility curve. This is located on the miscibility curve. So from here you can get the idea that what is the composition of E and R. Before I jump towards composition, let's try to locate this composition. By the way, just ignore these numbers here, they are of no use to you. They are overall you can see they are actually the scale points here, so just don't look at them. Just look for your composition at E and R, where this M tie line passing through M is joining the binodal or miscibility curve. So overall you can see here that at E, we can see that at E, at this E overall what is the composition. Let's look for this, like E is the extract, and extract, you know, it will be rich in furfural. So here furfural will be in higher amount, and that will be like somehow, like I can say somehow 92 or 93%, and then there will be somehow like ethylene glycol. In this ethylene glycol will be like at this line, and somehow ethylene glycol, you know, these horizontal lines, and it will be like 9%, and then you can see leftover will be the water. And let's look for the raffinate, you know, will be rich in water. So overall it will contain water in higher amount, large amount. Overall you can see here these lines at 45-degree angle represent the water. So overall water, I think it will be somehow like 45% or 44% here, because you see, no, not 44, like it will be like 55 or 56%, because there will be 60% water and then there is 50%, 40%, so it will be like 55% around. And others you can see there will be some small amount of furfural, and then there is ethylene glycol. So let's look at these values here. mean given to you exact values that water is 44 in extract, as we have located that was majorly furfural 87%, we have already seen that. Then there was small amount of like 9% we located, it is exactly 8.5%, there is ethylene glycol, and then leftover 4.5% is water. And similarly in raffinate you see like exactly 56%, as we have located there is 56% water, then there is small amount of not small amount, there is some sufficient amount of ethylene glycol, and then there is water. Some of you can think that there is still very large amount of ethylene glycol is present in this raffinate, so it is not extracted completely because you are talking about only one stage here. And we have discussed this, that usually on industrial scale for separation you need more than one stages for complete separation of this solute from feed towards solvent. Up to here you have solved 2 points, that was actually composition of extract and composition of raffinate. Now we are still left with the amounts, extract, amount of extract as well amount of raffinate. So let's find those. In order to calculate those, what you can do, you can just apply simple component balance on A and C. You can apply on any of these two, given like there was water as well as ethylene glycol and furfural, you have to apply actually on two of these, and you can calculate two unknown, that is amount of extract E and amount of raffinate. Up to here you have found composition, not amount, but now you have to find amount. So for that you can apply these balance. So I have just applied here for A and C, you can apply for A and B, you can apply for C and B, and you will get same answer. So overall for C, if I apply component balance for C, you know from where C is coming. If I just go back to this somewhere here, you can see from where C was coming from here, solvent. In this diagram you can see it is a solvent, and then it gets separated actually into E and R. We have just seen that it is part of both. In E, although it is in large amount, in R it is small, but still it is there. As well you can see, if I will apply balance for A is coming from feed here, its amount is coming from feed, and then it gets separated into extract and raffinate. So based on this I can apply for this balance. When you will apply balance, actually it will be like simply input is equal to output. Input is like here 200 gram, and output is a part of two components like two stream, extract and raffinate. So we will try to figure out what are those amounts. As well here there is no reaction, no accumulation, so simply input will be equal to output in extract plus output in raffinate. And same for A, it is like 55% here, 55 gram of this are getting in, and they are getting separated into extract and raffinate. So overall you can see here like input is 200, and that gets separated into extract and raffinate. And in extract how much C was there or furfural, this is 87%. So 87% in E plus 10% in R, because there it is 10%. And then for A, if you apply, it was at inlet 55, and then it gets separated into two parts, that is 0.045, or it is 4.45% in extract, and 56% in raffinate. So overall we have to solve these equations together, and for solving I have to multiply this equation of C, first equation with 5.6. I will get one equation, and that equation can be then just solved simultaneously, and finally you will get these answers of E as 220.6% and R as 79.4 gram. Sorry, they are not in percentage, they are in gram, they are amounts. Just solve them simultaneously and you will get this result. That's it. I think this was all about this example. So up to here in this lecture, actually we have discussed partially miscible solvent. Then we said that when you have partially miscible solvents, how you have to solve them, or how you have to use them for designing your liquid extraction equipment. You have to use triangular diagram for these system. and in those triangular diagram we have seen the detail what is apex, what is edge, and how you have to locate your data inside that diagram. And then when we have located our data, we have seen at binodal curve the one phase and two phases inside the diagram, and we also looked for tie lines. Then we looked for if we are given any mixture and that mixture is available inside that binodal curve, and then if you extend it towards extract and raffinate, what will be their composition. And finally we have solved a problem in which by given data we have used similar diagram and we calculated the amounts of extract and raffinate as well as their composition. At the end, I would like to thank this guy for providing very good self-explanatory images for these triangular diagrams. Thank you so much.